Okay, so this video goes over simplifying radicals, and this covers section 1.3, and 1.3 is in the OpenStax textbook. Before we talk about simplifying radicals, it's important that you understand what perfect squares are. Perfect squares are any number when you pick another number, multiply it by itself, and the product is one of these numbers. Now, these are the first 12 perfect squares. So, for example, 5 times 5 is 25. So, this is a perfect square I'm sure you're familiar with. Now, a lot of times when we say 5 to the second power, we take a shortcut and we use the word squared. So if you see that word squared being used, that is the same as to the second power. All of these are exponents. Now, for what we're going to be working with, I would highly recommend that you memorize the first perfect squares, at least to 12. So 12 squared is 144. All right, so simplifying radicals, let's talk about what a radical is. A radical is the symbol right here. So the square root is referred to, you use a radical for the square root. So for example, 9 squared equals 81. We know that the square root of 81 is 9. So basically the square root undoes the squared or the exponent of 2. So once we see inside the radical a perfect square, we know how to simplify it. So if you went on that chart with 81, then basically you know that the square root is 9. Now, this is not the same as dividing. Some students sometimes think that this is the same as dividing. It's an easy mistake to make, but it actually isn't. It's saying what number times itself is equal to 81, and that's 9. Now, right here, we use the exponent. I'm also going to show you, you can multiply it out just using those two numbers. Sometimes that might be easier to visualize because since we know 49 is 7 times 7, the square root of 49 is 7. Now notice it's very important that this is outside the radical. Sometimes students forget to take it outside the radical, so you want to make sure that you are back to the whole number. Okay, so let's do one more. This was the largest one on the list. And remember that 144 is 12 times 12. And that means the square root of 144 is 12. Okay, now that we can simplify any perfect square, of course, you can imagine that there's many numbers, for example, like 15, that is not a perfect square. So when you're thinking about simplifying radicals, you also want to be able to simplify radicals if there is a perfect square that is a factor of the number underneath the perfect square. So we have to use this rule, and this rule says if we use 15, we say that 5 times 3, square root of 5 times 3, 15 is equal to square root of 5 times the square root of 3. So essentially, we're going to use this because that means we can break down any radical into a product of two or more numbers. Okay, so if we look at 50, hopefully you notice that, oh yeah, 50 has a factor that is a perfect square. So we're always looking for the largest, but I'll show you, even if you don't get the largest, you can still simplify it. So 25 times 2, remember that 25 is our perfect square. So when we use the rule of multiplication, we have 50 equals the square root of 25 times 2, and we can break it down into each individual radical. Now notice this is outside the radical. The 5 is outside the radical because 25 is a perfect square. Now notice that 2, however, stays inside the radical because 2 is not a perfect square. So the way you read this is 5 root 2. So that's kind of a shortcut. So that basically means the 5 is multiplying the square root of 2. We don't put a multiplication sign. Notice we have this little dot as a multiplication sign. We know when they're next to each other, we automatically know that they're multiplying. Okay, so let's do, this is kind of the main meat of what we're doing. Let's take 72. Okay, now there's a couple ways to do it. You can actually make a little tree. You say 72, huh? Oh, that's 9 times 8. Now, sometimes you might not know you can even divide it by 2, but I'm going to show you we did not pick the largest perfect square on purpose, just so you can kind of see that it doesn't matter. And so what I'm going to do is simplify this to the square root of 9 times the square root of 8. Now, which one is the perfect square? Well, the perfect square is 3. So I'm going to write it right underneath here. And then we look at 8. Now, can we simplify 8? Can we simplify 8? Well, is there a perfect square that goes into 8? Well, there is 4 times 2. So we're going to do one more level of simplification. Now what we do is the square root of 4 is 2. I'm writing out the multiplication, but when we finish this final problem, we're actually not going to write any multiplication sign. So this is our final answer. And remember, we say 6 root 2. Now, the largest perfect square that goes in 72 is 36, which would actually kind of cut a couple steps here, but I just wanted to show you either way works. Okay, so 98. 98 is 49 times 2. Okay, so that means what we're going to do is we're going to rewrite this as the product of 49 and 2. Now, even if you wrote it backwards, let's say instead of writing 49 times 2, remember that this is the same as 2 times the square root of 2 times the square root of 49. Even if you wrote this way, and we're going to simplify this. Remember that this is 7, the square root of 49 is 7, and this is the square root of 2. Even if you write it like this, your final answer actually has to have the whole number in front. So the whole number is going to be in front, and then the square root of 2 is going to be here, and then we're going to read this as 7 root 2. Now, notice the 2 right here cannot be simplified. So that's what we're doing with these examples is we're simplifying what we can. So basically the square root of 98 is not the most simplified. This 7 times the square root of 2 is the most simplified. Okay, so now what we're going to do is add in variables. So sometimes we have to simplify with variables instead of using numbers. So if you look at example 1, we're going to actually combine numbers with the variables. So we're going to incorporate what we learned in section 3. So if you look at x to the fifth, just a quick reminder that the x to the fifth power is x times x times x times x times x. Okay, so if you haven't been doing math in a while, you might have forgot this. So this basically, we don't write the first power, but each one of these is the first power. So x to the fifth means basically you're multiplying it by itself 5 times. Okay, now when we are doing the square root, which we're going to come to in section 5, essentially what we're doing is we can use an exponent rule and we can just divide any even exponent by 2. Okay, so that is a way to look at it. Another way to look at it, so some people look at it visually, and I'm going to show you another way to look at it, so maybe it helps you. I'm going to just, now obviously when these exponents get really big, you actually have to start using the rule, but a way to visualize this is we look for pairs of 2, because remember that x times x is a perfect square. Because x times x is x squared. Notice that we have that x all by itself. So basically, another way of simplifying it is we basically can simplify this because it's a perfect square, simplify this as a perfect square, and we have x times x. But then we have that leftover x, and that's what makes this an odd. All the this is to the first power. So this would be the final answer. So this is another way to look at it besides this example here. Okay, so how do you do it with the shortcut is you just take 4 and you divide by 2 and you get this here. Okay, so but sometimes shortcuts are harder to remember than long cuts. This is a longer way of doing it. Okay, so now that we've kind of gone over this example, we have another example right here, and that's 18 times x to the fourth. Okay, so the first thing we're going to do is we're going to find the largest perfect square that goes into 18, which is 9. 9 times 2, and then x to the fourth. Now, 4 is even. So remember that 4 is even. So the shortcut for this is just to divide 4 by 2, the exponent only. And so now we are going to take this can be simplified to 3. This can be simplified to x squared, and then of course the 2 is left inside. Okay, so let's do a couple more examples so you can see how this works. So we're going to look at 48. So what is the largest perfect square that goes into 48? Well, you could do 4 times 12. It's not the largest one though, so but remember you could also do it um, in multiple steps if you like. And then we know that x to the sixth is even. So that means we can simplify which ones? We can simplify the 16 and we can simplify the x to the sixth power. And the 3 stays in the radical. Okay, so we got one more, and that is the next one is 75 times x to the fifth y to the second. Okay, so what is the largest perfect square that goes into 75? 25. Then we're going to break down x to the fifth into an even number. And remember, this is the one, we don't always write the one, but the one is there. And then we can simplify the following. So that means that this can be simplified, this can be simplified, and this can be simplified. Whatever I have left over will just stay in the radical. So this is simplified to 5, and this simplifies to x squared, and this simplifies to y. And then what we have left over is 3x. Now we rarely write the 1, but it would never be counted wrong if you wanted to write the 1. Okay, so the last section is not something you have to worry about too much because we're going to use this later, but I didn't want to finish this without talking about exponents a little bit more. So it turns out that every single square root or even other roots, we've only done the square root for right now, the square root can be changed into an exponent. So notice that you don't see any number here, but you see a number there. So basically, if you don't see a number in here, which is called the index, then that number is 2. So square root means that this should be a 2. Again, we don't write the 2. We usually just write, we don't write the 2. Now, can we simplify this? No. So it's as simplified as we can go. Okay, now, so basically, this is right here, as I said earlier, is the index, and this works out to be the denominator. Remember, I said that we don't always write that 1, but that 1 is there. And so the way we get there is the 1 is the exponent inside the radical, and the 2 is the index. Okay, so that is how we rewrite these with exponents. Okay, so this is an example. Rewrite the square root of x cubed using a rational exponent. So we're just using a rational exponent. Rational exponent is another word for fraction. Remember, if you don't see a number here, then we know that that's 2. So the 2 goes in the denominator and the 3 goes on the numerator. Okay, rewrite 7 as a rational exponent. So we know that the index here is 2. So this is 7 to the 1/2 power. Now, where does the 1 come from? Again, remember, if there is no exponent on a number, it actually is always 1. Again, we rarely write it, but it's there if you ever want to write it. Okay, and then finally it says rewrite x to the 5 halves in radical form. Okay, so the 2 is the index, and then the 5 is what's in the radical. So the 5 goes here, and the 2. And one way I remember this is that 2 is the root. Remember, we talked about square root. So that's how I remember this 2 is on the bottom. So think of the word root as a way for you to transfer. Now you might say, well, why are we even looking over this? Well, later on, as we learn, sometimes if you think about, sometimes you want your water in a water bottle and sometimes you want it in a glass. These are two forms of the same exact number, and sometimes it's easier to work with the exponent rather than the radical. So that's why we have both forms. Okay, well, if you made it till now, fantastic. Basically, these are the 5 things that we went over. The first thing is to remember what a perfect square is. When we are going to simplify a um, expression, we want to divide out a perfect square if we don't have a perfect square in the radical. And then we divide even exponents by 2. And then we write the simplified form outside the radical. And then finally, we can rewrite a radical as an exponent. So thank you for watching the video. And if you have any questions, please come see your instructor during office hours or go to the Math Success Center for help.